Hello, and I'm Jose Osa, and this is my video 3, in which we're going to be dealing with this proposition from the book, proposition 4.3.5, and we're going to try to prove it. And this proposition states that a subspace S of the real numbers is connected if and only if it is an interval. And we're going to use this definition of the interval that was given previously that says that a subset S of the real numbers is said to be an interval if it has the following property. If there's an element X that belongs to S, as well as an element Z that belongs to S, and an element Y that belongs to the real numbers, in such a way that Y is bigger than X and Y is smaller than Z, then this means that Y also belongs to S, because it would be between them and they would all belong to the real numbers. Working with this definition of an interval, we're going to try to prove this proposition with what we have from the book. So the first thing that we have to assume is that S is connected. So we can start by letting S be connected. And then this allows us to suppose that we can start with our definition of an interval. We can start by saying that suppose there's an element X that belongs in this S, as well as an element C that belongs with this S, in such a way that there exists a Y that lies between them. Now, for the sake of contradiction, in order to make this proof a little easier, we're going to assume that Y does not belong to S, which doesn't really make sense if we're trying to think about it intuitively, because if Y exists between X and Z in the real numbers, it feels like it should be part of the same interval. But let's try to prove this via contradiction. So if we let Y not belong to S, then we can deal with a specific subset of the real numbers, which is going to be this set defined from negative infinity to Y, open, not including Y, intersected with S. And that would mean that we would get everything from S because Y is not included in S. And the intersection of these numbers will give us anything from Y towards the X direction. And now if we think about it, and if we know that Y is not an S, then that means that this set right here is equal to a very similar looking set that includes Y intersected with S. And there's no issue with this because we know Y is not included in S, and we're intersecting it with S. So we still get S back from this on the side that goes towards the X value. Now, if we also look at this, we can see that this set right here is neither open nor closed. This is a clopin set. And so this means that neither the complement of this set is open and neither this set is open. It's just a clopin, And so now if we want to show that S is not connected, we have to verify two things about this clopin set. The first thing that we have to show about this clopin set is that this set is proper. And that means that if it is proper, then that means that we have an element Z that we defined earlier to belong in our set S, but the same element Z does not belong to our subset of negative infinity to Y intersected with S, because again, if we look at a number line and we have Y, Z, and X, this set tells us that we're going from this point to this direction. So this set doesn't include Z, which would in turn make this clopin set proper, because by the proper definition we have to have Z included in the overall S set. So that's the first thing we had to prove that we just proved about the set, that it is proper. Now we have to show that this same set is also non-empty. And this is very simple. We know it's non-empty because to the left of this y, which is not included in this set right here, we know that x exists in it. So we know that it's a non-empty set. So now that we have proven that this set is both proper and non-empty, then this would mean, by the connectedness definition, that S is not connected. Now, if we go back at our initial assumption, we let S be connected up here. So now we have arrived at a contradiction. So S has to be an interval. And if S is an interval, then that means that this Y that we decided that is not an S should be an S, because there's really no way to be dealing with the real numbers and this Y to not be included in this interval. So the important thing about this is that we're using this definition of an interval to show that if we have a set that belongs to the real numbers, then, and we have an interval in set, then that interval has to be connected. Because if you can't get from point X to point C without going through another point. For example, take the interval 0 to 1 from the real numbers. There's an infinitely amount of numbers in between those two things. So if you're going from one to the other, you have to go through another element, and that's it.